Welcome back, everyone. Ready for another deep dive?
Definitely. Always excited to explore new topics.
Today, it's all about metals. We'll be using excerpts from a textbook on machining and manufacturing processes. Ever wonder how a metal can be both strong and flexible? Or what makes some metals shine while others are dull?
It's amazing how materials science connects those everyday objects to the tiny world of atoms.
Exactly. So let's start there. Remember the basic model of the atom.
Oh, yeah, from high school science class. The nucleus with protons and neutrons.
Right, and those electrons zipping around.
Though it's actually more complex than that, right? Like, we used to picture electrons orbiting the nucleus like planets around the sun, but
Yeah, I remember learning about electron orbitals and energy levels.
right, electrons occupy specific energy levels, which helps explain how atoms absorb and emit energy. And that leads to things like light and color.
Okay, but how does all of that tiny stuff relate to big metal objects?
Well, because the way those atoms arrange themselves, their crystal structure, determines the metal's properties at a larger scale.
Oh, so like whether a metal is strong, flexible, or brittle.
Exactly. And how easily it can be machined. It's like a microscopic blueprint that influences the metal's macroscopic personality.
Okay, I like that. So if you imagine a crowd of people just milling about randomly versus a group of soldiers in a precise formation.
Ah, I see where you're going with this. The formation gives the soldier strength and purpose.
Yes, metals are similar. That atomic arrangement is key.
Great analogy. And just like different military formations serve different purposes, different crystal structures give different properties to metals.
And our source gives some cool examples, like bismuth. It forms those beautiful iridescent crystals.
You can even grow them at home.
Yeah.
Those rainbow hues come from a thin oxide layer that forms on the surface.
Oh, so it's reacting with the oxygen in the air.
Exactly. It's a reminder that even a little interaction with the environment can totally change a material's appearance.
It's like bismuth has a secret identity, depending on who it hangs out with.
That's a fun way to think about it. It shows how sensitive materials can be to their surroundings.
Then there's chromium. Super shiny. It resists corrosion because of, you guessed it, another thin oxide layer.
It's like a built-in force field against rust.
Makes sense why we see it everywhere, from shiny car parts to tools.
It's a reminder that sometimes the most valuable trait is a metal's ability to protect itself.
And then there's copper, famous for that reddish-brown color. What's wild is that you can actually find copper in its pure form in nature.
It's true, you might even stumble across it while hiking.
No way. I'll have to keep an eye out.
And it's that unique color and crystal structure that have made copper so valuable throughout history, from ancient tools and weapons to electrical wiring today.
Speaking of history, what about lead? I know it's not something we want to handle these days.
Yeah, for good reason. We know about its toxicity now, but it was used for a long time in plumbing, even cosmetics.
Yeah.
Lead is dense and easy to work with, and when added to glass, it actually adds shine and brilliance like in lead crystal.
But now, because of the health concerns, lead is carefully regulated.
Absolutely. It's a good reminder that our understanding of materials can change as we learn more.
Definitely. Okay, last one from our examples, magnesium. It's known for being super lightweight.
And strong, too. In its pure form, it forms these intricate, branch-like crystal structures called dendrites.
So it's like a microscopic metallic forest.
I like that. And because it's lightweight and strong, it's used in all sorts of industries: aerospace, automotive, even fireworks.
So we've seen how a metal's crystal structure is like its core personality. But we're clever. We figured out ways to enhance or even totally transform those properties.
Right. By alloying. It's like adding spices to a dish, introducing other elements to create something new with tailored properties.
It's like giving those metals superpowers. Take steel, for example. Essentially iron with a bit of carbon.
And the more carbon you add?
The stronger it gets, right?
Yes. But also less flexible. That's the trade-off with alloying. It's always a balancing act.
It's all about finding the right recipe. Speaking of recipes, think of cobalt as a pinch of temperature control.
Oh, how so?
Well, it helps reduce melting during welding or soldering. It makes those processes much smoother.
I see. It's like having a steady hand guiding the transformation of the metal.
And then there's titanium, a multitasker.
Yeah.
It's strong and lightweight on its own.
And incredibly versatile.
Right. As an additive, it acts as a deoxidizer in steelmaking.
Meaning?
It helps create cleaner, higher quality steel.
Oh, interesting. Like it has a purifying effect, getting rid of unwanted oxygen and impurities.
Exactly. And our source also mentions nitrogen being important in stainless steel,
To increase.
strength and corrosion resistance. It's perfect for anything that needs to stand up to tough conditions.
Makes sense. It's like giving the stainless steel a shield to protect it from the elements.
Okay, last ones. Tellurium and selenium. They're kind of the unsung heroes of machinability.
Mean me.
Adding even a tiny amount of them to steel makes it so much easier to cut and shape.
Ah, I see. They act as internal lubricants, reducing friction during machining.
Exactly. So we've gone from the atomic building blocks to the art of alloying.
Quite a journey.
And now let's talk about how we shape those materials into objects.
So, manufacturing techniques.
Each one uses a metal's unique properties to create things from massive structures to tiny components. Let's start with casting.
Casting is like making a Jell-O mold, but with molten metal. You heat it until it's liquid.
Pour it into a mold and let it cool. It's one of the oldest metalworking methods, right?
It is. It's still widely used today because it's simple and effective.
And you can create complex shapes.
Exactly. And our source mentioned different techniques, like sand casting, which uses compacted sand to make the mold.
Oh, and centrifugal casting.
Right. That one uses centrifugal force.
Like a super fast merry-go-round for molten metal.
Exactly. It creates things like pipes and tubes with perfectly even walls.
Okay, moving on from casting, let's talk about rolling.
Ah, yes, where metal is squeezed between giant rollers.
To thin it out and shape it.
Exactly. It's how we get those perfectly flat sheets of metal used in everything from cars to soda cans.
And there's hot rolling and cold rolling.
Right. Hot rolling is done at high temperatures. It's like softening dough before rolling it out.
And cold rolling.
That's at room temperature. It gives the metal a smooth finish and makes it stronger.
So cold rolling is like adding the finishing touches, making the metal sleek and ready to go.
Exactly.
Okay, now on to forging.
Where you shape metal by hammering or pressing it.
I can picture the sparks flying.
It creates incredibly strong and durable parts because it compresses the metal and refines its grain structure.
I bet. Our source mentioned a forging technique that uses a mandrel.
Ah, yes. It's basically an internal mold.
So you insert it into the heated metal and then hammer or press the metal around it.
Exactly. It creates hollow shapes with a consistent internal diameter.
Oh, I see. So it's perfect for making things like pipes.
Precisely.
Now for the futuristic stuff. 3D printing with metal.
Also known as additive manufacturing. It's building objects layer by layer from a digital model.
It's like something straight out of a sci-fi movie.
It allows for intricate designs and customized parts that would be nearly impossible to make with traditional methods.
Our source mentions specific 3D printing techniques for metals, like selective laser sintering, SLS.
And electron beam melting, or EBM.
Right.
With SLS, a high-powered laser fuses metal powder together layer by layer. EBM uses an electron beam to do the melting and fusing.
Wow, so it's like a laser beam versus an electron beam.
Exactly. EBM is particularly good for making parts with really intricate internal structures.
It's incredible how many different ways we've figured out to shape metal.
It really is, from ancient techniques to cutting-edge technology.
But before we move on to those techniques, let's talk about a super important tool, the FEC diagram.
The iron-carbon phase diagram.
It might sound intimidating, but I promise it's worth understanding.
It's basically a roadmap for understanding steel and cast iron.
It shows how different phases of iron and carbon coexist at various temperatures and compositions.
It's like a recipe book for metallurgists. It guides them in creating materials with specific properties by adjusting the temperature and the amount of carbon.
So by understanding this diagram, they can essentially cook up the exact type of steel they need.
Precisely. It's about controlling the microstructure of the metal, and that directly impacts the final properties.
Our source mentions all these different phases with pretty technical names.
Cementite, ferrite, austenite, pearlite, martensite.
Yeah, those. It's a lot to take in. But basically, each of those names describes a unique way that iron and carbon atoms are arranged.
And those different arrangements result in different properties for the metal.
Okay, that makes sense. So the FEC diagram is like a secret code for unlocking the full potential of iron and carbon.
I like that. It's like a map that leads to all sorts of possibilities.
Exactly. And now let's see how this knowledge is applied in the real world.
Let's look at some specific examples of how this diagram is used in practice. Our source compares a common structural steel, like 1.0038, with a high-performance stainless steel, like 1.4125.
Okay, so it's like comparing like a workhorse to a racehorse.
Exactly. Both are strong and capable, but one is for everyday tasks, the other's built for high performance.
I get it.
So 1.0038 with less carbon, it's perfect for, like, bridges and skyscrapers.
Makes sense.
But 1.4125, that one's packed with chromium and molybdenum. It's incredibly strong and corrosion resistant.
Oh, wow. So it's ideal for things like medical instruments or aerospace components?
Exactly. And even within stainless steel, there are trade-offs. Our source looks at 1.43001 and 1.4460.
What's the difference there?
Well, think about it like a chef's knife. One's easy to sharpen, but might rust faster, and the other's super durable, but harder to sharpen.
So different properties for different jobs.
Exactly. 1.4301 is easy to machine, less resistant to corrosion. 1.4460 is the opposite, tougher to work with, but resists corrosion like a champ.
Okay, that makes sense. And then there's cast iron. That feels like a whole different category.
It is. Cast iron is known for its high carbon content. Think about gray cast iron. It's got flake graphite.
What does that do?
Well, it acts as a lubricant, and it's used in things like engine blocks to dampen vibrations.
Interesting.
Then there's ductile iron. It's got nodular graphite, known for its strength and impact resistance.
So it's like comparing a shock absorber to a battering ram. Both cast iron, but different internal structures.
A perfect analogy. Then there's white cast iron, extremely hard and wear resistant. Think grinding balls, wear plates, things that need to withstand a lot of abuse.
Wow.
And we can't forget malleable iron. This one starts out as white cast iron, but it goes through heat treatment to become more flexible.
It's like taking a rigid metal and giving it yoga lessons.
Exactly. Malleable iron is used in things that need both strength and toughness, like car parts and agricultural equipment.
It's amazing how we can transform these metals so much.
It is. And now let's dive deeper into those manufacturing processes we touched on earlier.
Yes. Let's get into the specifics. Casting first, right? What else is there to know about it besides pouring molten metal into molds?
Well, it's like creating a metal sculpture. You heat the metal until it's liquid, pour it into a mold, let it solidify. Sand casting is a classic example. They use compacted sand for the mold, then break it away once the metal's cooled.
It seems so simple, but it's still used so widely.
It works.
Yeah.
Sand casting is relatively cheap and can be used to create a huge range of shapes and sizes.
What about centrifugal casting? I'm curious about that one.
So that one uses centrifugal force. It's like the molten metal is on a high-speed merry-go-round.
And that creates.
Cylindrical objects like pipes and tubes with even wall thickness.
So it ensures a really balanced and consistent product.
Precisely.
Okay, moving on to rolling. I picture those massive rollers pressing metal sheets thinner and thinner.
That's it. It's like a giant rolling pin for metal. We can create sheets and strips of different thicknesses and surface finishes.
We talked about hot and cold rolling, and I'm wondering, is temperature the only difference?
Temperature is a big part of it. Hot rolling happens above the metal's recrystallization temperature.
I mean,
It makes the metal more malleable, kind of like warming up dough before rolling it out. This is great for large structural components where the exact dimensions aren't super critical.
gotcha. And cold rolling.
That happens at or near room temperature. It's like giving the metal a final polish, a refinement.
Makes sense.
It results in thinner sheets with smoother surfaces and more precise dimensions.
Okay, so it's for those situations where looks and precision matter.
Exactly.
Now, forging that seems like the most hands-on of the techniques we've talked about.
It is shaping metal with hammering or pressing.
I can almost hear that clang of the hammer on the metal.
It creates really strong, durable parts. All that hammering compresses the metal, refines the grain structure.
So it's getting stronger with every hit.
In a way, yes. We mentioned a forging technique that uses a mandrel earlier. What exactly is a mandrel?
It's like an internal mold. So you heat up the metal, put the mandrel inside, and then hammer or press the metal around it.
Ah, I see. And that's how you create those hollow shapes.
Fascinating. Okay, now the really cool stuff. Additive manufacturing, or 3D printing with metal.
It's like building an object piece by piece from a digital blueprint.
It still feels so futuristic to me.
It's amazing what we can do now. It allows for such intricate designs and customized parts.
Right. We mentioned SLS and EBM earlier.
Yeah.
Those are specific types of 3D printing for metals.
Yes, selective laser sintering and electron beam melting.
Can you remind me how those work?
Sure. With SLS, you use a powerful laser to fuse metal powder together, layer by layer, based on that digital design.
And EBM?
Similar, but it uses a high-energy electron beam instead of a laser. It's really good for parts that need to be super strong and have complex internal structures.
Okay, so it's a choice between laser or electron beam, depending on what you need the final part to do.
Exactly. And, from ancient casting to this cutting-edge 3D printing, it's incredible how many different ways we figured out to work with metal.
It really shows how innovative humans are.
It does. But before we get too far ahead of ourselves, remember that FEC diagram we talked about earlier?
The iron-carbon phase diagram. It's like a roadmap for understanding how different phases of iron and carbon work together,
It's so important, especially for understanding steel and cast iron.
which are everywhere.
Right. So the diagram shows us how different phases with their different properties exist at different temperatures and compositions. It's how metallurgists know what to expect when they're working with these metals.
Okay, I think I'm starting to get it. It's about predicting how the metal will behave under certain conditions, right?
Precisely.
And all those technical terms we mentioned, austenite, ferrite, cementite, and so on, they're basically describing those different phases with their different arrangements of iron and carbon atoms.
Exactly.
Different arrangements mean different properties.
Exactly. Think of it this way. It's like having a toolbox full of different types of steel, each with its own strengths and weaknesses.
And the FEC diagram tells us which tool to use for the job.
Perfect analogy.
So instead of getting lost in the details of each phase, let's focus on how this diagram helps us understand the different types of steel used every day.
Let's do it. It's a special type of intermetallic compound. It forms within the superalloy's matrix.
Okay.
So you end up with this network of tiny, strong particles, and those particles actually make it harder for dislocations to move around.
Oh, I see. So they're like tiny roadblocks making the whole structure stronger.
Exactly. And the best part is gamma prime is stable at those high temperatures, so the superalloy stays strong even when things get really hot.
Makes sense. Our source talked about how you can fine-tune the properties of superalloys by adding other elements,
Oh, absolutely. Each element has its role.
like chromium.
Chromium is key for resisting oxidation. It forms a protective oxide layer that prevents the metal from deteriorating at those super high temperatures.
So it's like a suit of armor, protecting it from heat and oxygen.
I like that analogy. And then you've got aluminum. It combines with nickel to form those gamma prime particles we talked about.
Right, the ones that give it that high temperature strength.
Exactly. And then there's titanium.
Titanium, okay. We know it's strong and lightweight on its own, but what does it do in a superall?
It boosts strength and creep resistance. It helps create those extra strengthening phases, and it promotes a finer grain structure.
So it's like a personal trainer for the superalloy, making it even tougher.
Aha, I love it. And titanium also makes the superalloy easier to weld, which is important when you're building those complex engine components.
Right, you don't want things falling apart at those temperatures.
Definitely not. So as you can see, creating a superalloy is really a balancing act.
Carefully selecting each element.
Exactly. It's like a metallurgical recipe. You have to get the proportions just right to achieve the properties you need.
And it sounds like there's more to it than just picking the elements.
Oh, yeah. These superalloys go through a lot of processing: melting, casting, forging, heat treatments, surfic treatments.
What's the purpose of all of that?
Well, all those steps help refine the alloy's microstructure, optimize the grain size, and make sure those strengthening phases are evenly distributed. It's about making sure the superalloy can handle those extreme conditions it's going to face.
So it's like a training regimen, getting it ready for peak performance.
Precisely. And just like athletes need specialized equipment, superalloys often have special coatings applied to further enhance their performance.
Wow, that's impressive.
It is. It's remarkable what we can do now with these materials.
Agreed. It's really a testament to the ingenuity and skill of the people who work in this field.
Absolutely.
Okay, well, I think that's a good place to wrap up our deep dive. We started with atoms and ended up exploring materials that can withstand the inside of a jet engine.
From the microscopic to the macroscopic, it's amazing how interconnected it all is.
Right, and it all comes back to those basic principles of material science.
Understanding the relationship between structure, processing, and properties.
Exactly. Well, I hope everyone listening enjoyed our deep dive into the world of metals.
Me too. Always fun to explore this stuff.
Until next time, keep asking questions, stay curious, and keep learning.